My name is Philip Di Melo, and today we will talk about modeling of the universe based on modern discoveries. Also, we can say that we will talk today about new answers to old problems, and this presentation is based on the interview I gave to Scientific American in April 16, 2024. The old questions are, but not limited to the following. Is the universe finite? Is time finite? What happened before the Big Bang? And other questions. And after many centuries of thought, humanity has still not arrived at conclusive answers to these questions. There remains no clear or definitive evidence that the universe is either finite or infinite, although there are some intriguing arguments or proposed theories on both sides. The great thing about this mystery, however, is that due to the nature of the universe, we may never be able to truly know the answer. Okay, so this is quite sounds pessimistic, means that we will never actually be able to know the answer to these questions, but let us just think to be more optimistic and show some possibilities to answer this question based on some discoveries that actually have been made. One of the major discoveries that actually shed light on the shape of the universe is the Poincare conjecture. Poincare conjecture goes back to 1904 and was made by a famous and one of the best mathematicians at all time, Henry Poincare. Poincare conjecture looks quite simple. You just take a body, which is we call compact body, which is like bounded, and it's simply connected. So it means that I take a point 1 and point 2, and I can just make a path, continuous path from point A to point B, and that it is necessarily homomorphic to the three-dimensional sphere. What does it mean homomorphic? It means it is a sphere, or it can be transformed to that sphere. And it is also has another requirement that any loop in this space can be contracted, is contractible to a point. So for example, we take let's say, donut, and we take a mug, and actually they are the same from this point of view, because it can be transformed one to another, and so forth. It has holes here, but this object, for instance, torus, cannot be transformed to the sphere, so it's not homomorphic. So in other words, if you take, for example, a mug and goes to a donut, you can go back and forth. You can have these transformations that make us think that actually all these objects are similar. Now, when we talk about the contractible to a point, it is true. If we take on, as let's say, a sphere, you take any loop, you can actually contract this to a single point. This is perfectly satisfies the Poincare requirements. However, it looks like very simple, but the real proof, was not delivered for many, many years, over 100 years. So it took us 100 years to prove this conjecture, and one of the most significant efforts in this direction was made by Richard Hamilton from Columbia University with his Ricci flows that actually govern the transformation from one object to another. And a brilliant Russian mathematician, Perelman, who actually gave a generalized proof, because in Ricci flow we can have singularities, and he can he proved that these singularities can be removed, and we call Ricci flows with surgery. So actually, the whole strict mathematical proof was given by Perelman, and therefore now this called theorem, Poincare-Perelman theorem, or better to say, it is Poincare-Hamilton-Perelman theorem. Now, what does it mean that if you take, for instance, this kind of body, and it has no holes, no edges, and any loop can be contracted to a single point, which satisfies the Poincare conjecture, this body is actually homomorphic or can be transformed to this to the sphere. And we talk about a three-dimensional sphere in a four-dimensional space. So what does it mean three-dimensional? It is difficult to imagine this three-dimensional sphere in a four-dimensional space. We can easily imagine, for example, two-dimensional sphere. Two-dimensional sphere, if they take a basketball ball, it is a sphere of, it is a surface of this ball in a three-dimensional place. We understand this. And there's, let's say, one-dimensional sphere in a two-dimensional space. It is just to take a piece of paper and draw a circle. That will be a one-dimensional sphere in a two-dimensional space, which is just a piece of paper. But three-dimensional is not so easy to understand, three-dimensional sphere. And this is what exactly I told before, that when you take just two objects with a singularity, the singular point, for example, then it caused some problem with the proof of the Poincare conjecture, and that Perelman actually made this kind of surgery. So he cut this, and he proved that it is perfectly legitimate action in mathematics, and that he connected these two balls and then transformed them to a single ball, a single three-dimensional sphere. That's what it is. What happened is that actually one of the applications of the conjecture, or Poincare conjecture, with is in, for instance, it sheds light on the shape of the universe. It comes up that the universe can be presented as a three-dimensional sphere in a four-dimensional place. N is here 3, so it is governed by this equation. The also conclusion on that if since it is satisfied the Poincare-Hamilton-Perelman theorem, that any traveler that travels in the universe, it goes, let's say, straight to space, it will come back to the same point of his departure or her departure. But actually, what happens also, that the Poincare-Perelman theorem can be also rewritten in as a system of equations with distributions. So what does it mean, distributions? Distributions, they have singular support, so they show the singularities of possible singularities. And what happened is that these equations show actually that the universe can be viewed as an inflated and deflated balloon bouncing between two singular planes given by Dirac's function. That's what can be proved. I just skip this mathematics here, and I will just show you how it looks like. So suppose you have two planes. One is x minus 0, x plus 0. So it shows that if this plane is can be considered as boundaries where the universe is getting from just single point on the plane. This is a Big Bang plane, I would say that. And then it is inflates to the maximum dimension here at the center, and then start to deflate. It collapses again on coming closer to this plane, and when it hit the plane, this plane gives you another Big Bang. So this model shows that actually Big Bangs is not a Big Bang, is not only one that happened at some point, at some or at different points in some time or different times. Actually, this situation shows that Big Bangs are just periodic. They come up, they can go on and on to infinity, because it's just balloon bouncing between two planes. That's what it shows. And numerical modeling shows, I just put here some uncertainties that can happen, but the idea is that you can see that the radius of this three-dimensional, the sphere that bouncing between these two planes, they start with like 0 at the Big Bang, and then it becomes here maximum at this point, and then the universe starts to collapse, and it goes to 0 again, and coming to the upper plane. Now, what happens is that when you just you just stretch this, present it as a continuous process, periodic, you can see that actually we can look at the dynamic of the universe as the Big Bang that creates the universe that expands to the point, then collapsing, that another Big Bang, and so forth and so forth, and it goes on and on and on, giving time actually infinite. Okay, now what happens is that when taken in terms of space, the expanding universe comes from singularity, that it is expands to some critical point when the universe is quite large, and then start to collapse and reaches again the singularity that gives you again the Big Bang and the expansion of the universe. Now, it is also interesting to calculate the rate of expansion of the universe. And you can see that it's highly nonlinear. So expansion of the universe is very, very high at the beginning of at the birth of the universe. Then expansion becomes much smaller at older ages of the universe, and it is just flattens flattens to when it is a maximum size. And then it starts to deflation, or universe start to collapse to a single point. So this is the rate of expansion of the universe. So it is positive here because it is rate of expansion. It is positive, so means that the universe expands, and this is the rate of expansion is negative, means that this universe collapsing to a point, and the collapsing rate of collapsing is very high as well. So when it comes to the point when the universe starts to collapse, it becomes collapsing more and more and more and more. Okay, so what happens is that in the spectrum, so we know that the universe has current universe has red spectrum. We call it red universe because the problem is that when you have expansion, so the wavelengths is getting bigger compared to the normal situation when, for example, the distance between source and observer is the same. So in this case, the lambda becomes higher and higher, and this corresponds to red universe. So this is large wavelengths correspond to the red universe. However, when it is collapsing, the wavelengths become shorter, and when the universe starts to collapse, it is the color of the universe will be violet. So in other words, it will be shifted towards the left margin of the visible spectrum, so becomes the universe becomes violet. Now we can compute also acceleration of the universe, and this graph shows that that it is also acceleration of the universe is so expansion is not uniform, so it's not coming with the same velocity expansion. It is actually it follows this curve. So the acceleration here, for example, negative, and it's growing, means that we have derivative here is so this means that the universe is correspond to expansion, and then it is collapsing of the universe. It correspond to this acceleration. So this is also shows that the acceleration of the universe is, so universe cannot be presented as a just constant expansion or constant collapse. So this highly non-linear situation. Now what happened is that we also did some work on machine learning, find out what other features, except that it is governed by the Poincare-Hamilton-Perelman conjecture, what can other possibilities, what kind of characteristics of the universe can also affect the dynamics of the universe. So we did, to answer this question, we did computation using machine learning and feature engineering. So what does it mean, feature engineering? I'm not going to go into details of that, but feature engineering allows us to identify the most important characteristic compared to other characteristics that influence the process. And what we found out that actually the gray energy and gray matter plays the most important role in the dynamic of the universe. Now, I would like just to remind you that there is a quite big attention to understanding of gray matter and gray energy because they occupy a large space in the universe. And it was lots of research, and it is still, there is many questions about that. So our result is a preliminary. We cannot say that it is the culprit. This is what exactly influences, and this is mechanism, and gray matter and gray energy are built in the universe as, to control the evolution of the universe. But our preliminary results show that gray matter and gray energy plays a very important role in the dynamic of the universe. All right, thank you.